sent them out to the class. First of all, I put some supplementary problems for chapter 2. Hopefully by now you've already worked the chapter 1 problems. Yeah, and they were okay, right? They're pretty simple. Chapter 2 you'll see is a bit more difficult. And the chapters they'll get a little bit more difficult beyond chapter 2, but once we get to chapter 4, that's about as difficult it's going to get. And then it'll sort of tailor off a little bit and get a little bit easier. But we're going to get a little more difficult from chapter 1, certainly. Um, So I put some supplementary problems. You know, I think if you're able to do the homework problems that are in the chapter and you have no difficulty with them at all, and we'll actually work through some in class, you'll be okay with the exam. But if you feel like you need some extra practice, I have some supplemental problems that you can work through as well. And the solutions I've also posted. Um, so I have these problems. They're PDF attached to that. And then if you go to the screencast here, you can find solutions to those problems. It's right up top. It'll be sort of right after today's screencast, which I put online every day. So you'll see that in that playlist there. I also posted an announcement about a help session. I'm having a help session for the Physics 101 class, but and eventually those two classes, this class and Physics 101, will diverge quite a bit actually. But right now they're sort of about the same, except that they don't do calculus. So where we do derivatives and stuff like that, they won't do. So I'm having a help session for them. But if you have questions, if you come and you have questions about some of the calculus problems, I can probably answer those as well. I just don't want to dwell on them the entire time because it's really for the 101 students. Okay, so that help session is on Thursday from 3 to 4. I'll have it now until the end of the semester, every Thursday, unless it's a holiday or whatever. Okay, y'all are welcome to come, but towards the end of the semester, the two classes will diverge, and it won't really benefit you to come. I'll let you know when that is. Okay? You doing okay this morning? No, Brooke? Brooke, did you say no? No. Okay. I kind of had a long morning. We had a rough night. Cat was howling. Oh, my wife came in late. She had gone to this thing. And my daughter was coughing like at midnight. So I got like 3 hours of sleep. Like, despite my advice to you, and it's good advice to get 8 hours of sleep a night, I did not do that last night. So I've been up since 12:30. All right. Um, let's see. Let's do a few clicker questions, just sort of to start out the day. It should be pretty basic for you. You and your dog go for a walk to the park. On your way, the dog takes many side trips to chase squirrels or examine fire hydrants. When you arrive at the park, do you and your dog have the same displacement? Yes or no? By the way, these are in the back of your book if you want to follow along there in that appendix. Yes or no? Do you have the same displacement? Sure. All right, let's see. I'll stop here in just a few seconds. I'll stop at 50. Hey, Gary. Still have a few of y'all that aren't registered, by the way, your clickers. I'll post all the points that you have up to this point, and then if you're not registered, you just send me your ID number. Not a big deal. It'll get post dated when I do register it. So yes is the right answer. Uh, the dog, even though it runs a lot more, you still have the same displacement because you have the same what and what. That's right, Claire. The same starting and finishing point, the same initial and final positions, which is how we define displacement. You've not traveled the same distance, however. If the position of a car is 0, does its speed have to be 0? If the position of a car is 0, does its speed have to be 0? All right, I'll stop at 40 seconds, 40 seconds. Okay, B is right. You know, we set where the position equal to 0 is. We say this is 0 or that's 0. So that's not necessarily related to the speed. You can move through a position equal to 0 with a non-zero speed. We'll see that particularly in this chapter as we're working through problems. But you always set where your position equals 0 is. You set your coordinate system, right? You set your frame of reference and your coordinate system. Does the odometer in a car measure distance or displacement? Stop at 25, 25. Okay, A is the right answer. If it were to measure displacement, it would include the direction. So it doesn't do both. No, I've never seen an odometer that includes direction. And does the speedometer measure velocity or speed? I'll stop at 20 seconds, 20 seconds. B is the right answer. And have we got an average speed yet? I forget. We cover average speed? We did. All right, let's try this one. This one's a little trickier. You drive for 30 minutes at 30 miles an hour, and then for 30 minutes at 50 miles an hour. What is your average speed for the whole trip? Remember, our average speed was the total distance divided by the total time. Is your average speed more than 40, equal to 40, or less than 40? Doing pretty well, most of you. I'm going to stop at 55, 55. All right, very good. B is the right answer. This is a little tricky, but a couple ways you could do this. You could say, I'm traveling the same amount of time at these two speeds, so I can just take the average of them. And if that doesn't, I can say 30 plus 50 divided by 2, that's equal to 40. Only because I'm traveling the same amount of time for each of the speeds, for each of the 30 miles an hour and the 50 miles an hour. But if that doesn't jive with you very well, you can also just return to our definition of average speed, which is d over t, right? I can find the distance for this scenario, 30 minutes at 30 miles an hour. How many? Yeah, right. So it's traveling at this speed. There's no time for acceleration. That's what you're asking, right? At 30 miles an hour, 30 minutes, how far do you travel, Corinne? You're about 15, right? Half an hour at 30 miles an hour, you travel a distance of 15 miles. Uh, 30 minutes at 50 miles an hour, you travel how far? 25, right? So I can say I have 25 plus 15 miles divided by 30 minutes plus 30 minutes, that's 1 hour. And so that's 40 miles an hour. So you can go through that little calculation if you want. But if you're traveling the speeds for equal amounts of time, you can just average them. 30 plus 50 is 80 divided by 2, that's equal to 40. You drive 4 miles at 30 miles an hour, then another 4 miles at 50 miles an hour. What is your average speed for the whole 8-mile trip? Is it more than 40 miles an hour, equal to 40, or less than 40 miles an hour? Think about the easy way that we did this problem before, and how would you apply it to this problem? shoot for about 10 more seconds. Stopping about 55, 55. Just guess if you're not sure. Okay, so here I'm traveling at 30 miles an hour for greater amount of time, equal amount of time, or a lesser amount of time than I'm traveling at 50 miles an hour. Which is it? Greater amount of time because I'm traveling the same distance, but I'm going more slowly, right? So at 30 miles an hour, I'm traveling for a greater amount of time. You follow me? I'm going along at 30 miles an hour. My dad drove really slow. And like whenever he would drive, he had a line of cars about 12 cars deep, right? It takes him a lot longer to travel 10 miles than it does for somebody zooming along at like 60 miles an hour. You follow me? It just takes longer to travel a distance if you're going more slowly. So it's going to take you longer to travel 4 miles at 30 miles an hour than it is for you to travel 4 miles at 50 miles an hour. If you don't believe me, you can calculate it. It's pretty simple, right? Uh, V is d over t. So I can say t is d over v. At 30 miles an hour, that's 30, or excuse me, 4 divided by 30 miles per hour. That's 4 over 30. It's 2 over 15. We're just leaving a fraction. 2 over 15 hours, 2/15ths of an hour. And then you can do the same for the 50 miles an hour. It's going to be 4 over 50, which is going to be 2 over 2/25ths of an hour. All right. So more time traveling at the slower speed. So that means what's going to happen to the average speed? I'll let y'all try this again. The answer is not B. It's either A or C. Which is it? If I'm traveling for a longer time at 30 miles an hour, what happens to my average speed? All right, I'm going to stop at 25, 25. C is right. Your average is going to be skewed less than 40 miles an hour. All right. Oh, good job, the 8 of you that got that right. We'll come back to this. Okay, we're going to look now at instantaneous velocity. We've defined average velocity, and we're going to look at instantaneous velocity, and that's where we'll begin to see some of the calculus coming into this chapter, the definitions of derivatives and integrals, and how they apply to things moving, to kinematics. The instantaneous velocity is just the velocity at a particular time. Literally, the velocity at an instant. That's where instantaneous comes about at a particular instant. This is simply, or rather, I'm sorry. This does not match up with my notes. Sorry, let me figure out what do the blanks mean. A something in a give the. Do you know? Did you? Yeah. y- Oh no, this doesn't match up with my notes. I'm sorry. We're just gonna cross it out. I don't know what happened. It's just the average velocity. Remember our average velocity we defined as delta x over delta t, but with delta t, instead of being an interval of time, we're going to let delta t collapse down to an instant of time. So if we're looking at a particular instant of time, what is delta t going to equal? It's going to equal 0 because at an instant of time, a particular instant of time, that delta t is equal to 0. There is no delta t, it's just an instant. So, but we're going to have delta t equal to, or actually approaching, the value 0. So that comes about our definition here for the instantaneous velocity. It's the limit, and some of you are in Calc 1 this semester, but it's the limit as delta t approaches 0. Those of you in Calc 1, y'all doing limits right now? Yeah, so it's the limit as delta t approaches 0 of delta x over delta t. Right, we saw this definition last chapter too, and this, of course, is just the definition of the derivative. So the instantaneous velocity is the first derivative of the position function. Um, in a nonlinear graph, oh, and by the way, the derivative, remember, describes what physical quantity about a graph. The derivative of a function, the derivative of a plotted function describes what quantity about that function. The rate of change, something else that I'm looking, like if you graph it on a plot, the derivative is the what of that graph? The slope, right, which is the rate of change of that graph. Okay, so the derivative represents the slope. In a nonlinear graph, such as the one below here I'll show you, the slope of the tangent line, remember slope is just a run-of-the-mill word for derivative. The slope of the tangent line is equal to v, the instantaneous velocity. May I go down? All right. So here I have this graph. If I want to know the velocity at a particular point, or first of all, if I want to know the average velocity, remember what we'd do is we'd pick a point here and here, and that time interval would be our delta t, and then we'd find the slope of that line. But when I'm finding the instantaneous velocity, I'm going to let that time interval collapse down to a particular point in time. So I'm going to let that delta t approach 0, and then say I want to know the instantaneous velocity at this particular point, then I will find the slope of that graph at that particular point, and the slope of the graph is the slope of the tangent line. Didn't we cover tangent lines in chapter 1? Did I go over that briefly? No, let me just sort of cover it here. So this is our average velocity. This is our instantaneous velocity at a particular instant. You know, there is a mathematical definition for tangent lines. I don't know what it is. I forget. But I like to think of it as like a seesaw or something balancing. Let's say that we have a hill like this, and we want to balance a board on it, like that. That board is tangent to that curve. It has something to do, I forget, with at points on the line that it's equidistant from points on the curve. Doesn't really matter. But you can sort of visualize what the tangent line is. So for example, if I were going to draw the tangent line at this point, it would look more like this. Or if I were going to draw the tangent line at this point over here, it would look like this. You sort of visualize what the tangent line looks like. It's tangent to the curve. You will have some questions in your homework and on the exam where you have to estimate what is the slope of the tangent line. And we'll do one. Let's see, this next one might be that. Yeah, here we go. This graph represents the motion of a particle, and I want to know the particle's instantaneous velocity at t equal 4 seconds. Now you don't have the function. If you had the function, you could just take the derivative and find that velocity. But here I just have the graph of the function, and I want to know what is the instantaneous velocity at t equal 4 seconds. So you want to estimate what is the tangent line to that graph at this point, and then find the slope of that tangent line. Whenever you encounter a multiple choice problem, you should always look at the answers that are not the answers, right? So you have some options up there that are clearly not the case, so you can just get rid of those right away. If you finish this one, you can go on to the next problem. I'll open up the clicker for that in just a second, where you're looking for the average velocity between t equals 0 and 2 seconds. Give you about 10 more seconds. going to stop at 1:30. Okay, looks like we're all over the board here, but it is either A or B. I'm going to go ahead and draw my tangent line here. If I draw my tangent line, see, it's going to look something like this. This curve is actually pretty straight at the 4-second mark, so my tangent line is going to look something like this. And then to find the slope, I just draw my triangle like this. Y'all have done this in lab, if you haven't been in lab yet this week, where you find the slope of a line. Slope is rise over run, right? What's my rise on this graph? My rise is 6. My run is what? 2, right? So my slope then is going to be 3 meters per second. Listen, I know why you guys put B. Does anybody know why you put B? That was incorrect. I'm pretty sure I know why you did B. Why'd you do it? You counted the squares, right? That's very, very bad to count the squares. You should always look at the axis because the tick marks don't always represent whole numbers. Sydney, you have a question? The rise is 6 because I'm taking this point to this point to find my slope, and so I have 3 minus negative 3. Since each of these squares represents a whole number 1, 1, 2, 3, 4, 5, 6. Is that clear? All right. Be careful with that. I know it's a tendency to count the squares on graphs, but often that doesn't work well. So A is the right answer. B is a good wrong answer, but it's still wrong. All right, let's go ahead. I'm going to leave the graph up here so you can see it. But on the next question, I asked for the average velocity between t equals 0 and t equal 2 seconds. What is the average velocity between t equals 0 and t equal 2 seconds? And these are your options. It's on the next page, I think, for y'all, that question. What is the average velocity between t equals 0 and t equals 2 seconds? All right, doing pretty well. I'm going to stop at about 1 minute, so about 10 seconds left. Pretty sure that's right, yeah. So you can do this a couple ways. Let's just pull the data points off. I'm going between these 2 points. Our average velocity is delta x over delta t. That's going to be x final, which is -4, minus x initial, which is -1, divided by 2 minus 0, that's my time interval. So that's -3 over 2, that's -1.5, which was B. B is the right answer. You definitely will have a problem on the exam where I give you a plot and I ask you to interpret it. It could be something as simple as this, but you'll also have problems, which we'll encounter today or Friday, where I give you not only the plot, but I also give you the function that describes the plot, and you have to do some things with that. But we'll get to that soon. It's okay with this? Yeah. All right. Um, Now let's move on and we'll define acceleration. This just describes how the velocity changes with time. And we define the average acceleration. You know, we really define the average acceleration and the average velocity in order to further define the instantaneous velocity and acceleration, because those things, you know, are defined based on the definition of the average. So the average acceleration is just like we had for average velocity. It's going to be delta v over delta t. That's v final minus v initial divided by our elapsed time. Of course, taking t equals 0 is our initial time. So simply, like if I had an initial velocity of 10 meters per second, final velocity is 20 meters per second, I would just say 20 minus 10 divided by my time interval, which is 2 minus 0. So that's 10 over 2, or 5 meters per second squared. That's really simple, right? Let me make a little sort of cement this in your mind about what the sign of the acceleration means. Because if I tell you that you have a negative acceleration, what does that typically mean to you? Right, that you're slowing down. But that's not true. For you to have a negative acceleration does not mean that you're slowing down. Because you're thinking a negative implies deceleration. But the negative does not mean deceleration at all. Instead, when we're talking about vectors, the negative means what? Yeah, backwards, left or down, or whatever it is our negative axis is. So the negative refers to a direction, not to a change in rate, whether it's increasing or decreasing. So just a little couple rules. I just emphasize it because students often have trouble with this because they always think negative acceleration means deceleration, and that's not the case. Sometimes it's the case, but not always. All right, if the velocity and the acceleration are in the same direction, the speed increases. If the velocity and the acceleration are in opposite directions, the speed decreases. All right, so we can have a couple of examples. For example, here, if they're in the same direction, I can have a positive v and a positive a. That would mean that my speed would increase. I could also have a negative v and a negative a. That is, an object that's moving in the negative direction, so it has a negative v, and it's also accelerating in the negative direction, so a negative a. It would be like if I walked in this direction and I sped up, right? This is also increasing. Here, in the second scenario, I can have either a positive v and a negative a, right? In that case, it's slowing down. Or I can have a negative v and a positive a. All right, so in this case, I have a negative acceleration and it is decreasing. And here I have a positive acceleration and it's still decreasing in speed. It's slowing down. So positive or negative acceleration can mean either speeding up or slowing down. It depends on the direction of the velocity. Okay. So acceleration can be um, positive when the object is decelerating, and it can be negative even when the object is speeding up. So just, I mean, we can look at these numbers. If I have VF is negative 20 and VI is negative 10, what direction? Is it moving to the left or the right, this object? It's moving to the left, right? It's moving to the left because this sign says that it's in the negative direction. What is happening to the speed here? Is it increasing or decreasing? It's increasing. It was going a speed of 10 meters per second. Now it's going a speed of 20 meters per second. All right. So what is the sign of the acceleration in this case? Is it positive or negative? Is it slowing down or speeding up? It's speeding up. So is the acceleration in the same or the opposite direction as the velocity? Same. Very good. It's in the same direction. When they're in the same direction, it speeds up. When they're in opposite directions, it slows down. All right. So here, uh, we can just calculate the average acceleration. It's going to be VF minus VI, negative 20 minus a negative 10 divided by 2. That's negative 10 over 2. That's negative 5 meters per second squared. So this thing is speeding up in the negative direction, and it has a negative acceleration. Let's think about how that graphs. Let's see. Can I go down from here, y'all? So the car has a negative acceleration, but it's actually speeding up. I want you to graph this scenario. If you were to graph this, what would the velocity versus time graph look like? What would the velocity versus time graph look like for that scenario? A v versus t graph. First of all, which quadrant would it be in? The first or the fourth quadrant? It's going to be in the fourth quadrant, right? Because my velocities are negative. And on the y-axis here, this direction is negative, all right? So is my slope of this graph that I plot down here, is it going to be positive or negative? The slope of a v versus t graph gives us what? The acceleration. And we know that our acceleration is what, positive or negative? Negative, right. So the slope of the graph that we draw here is going to be positive or negative? Negative, right. So that means that it's either going to look like this, the blue line, or it's going to look like this, the red line. Which is it? The red line, right. And if you look at the numbers, I mean, it makes sense, right? I start at -10, and then I go to -20. That's what it looks like. It's important, though, because we're going to do a lot of interpretation of these type graphs, and you'll definitely see that on the exam, which is a week from Friday. All right. We're only going to consider particles that have constant acceleration. That means that the average acceleration will always equal the instantaneous acceleration. So never, ever, ever will we see a v versus t function that looks like this, for example, where over a certain time interval, the average acceleration might be some value, but at a particular instant, the instantaneous acceleration will be different from that. You follow me on that? Like if I looked at this graph, the average acceleration between these 2 points, I would list like that. But the instantaneous, say at this point, would look like that. So those are different. But we're not going to encounter that, at least not numerically. We'll see it. Well, no, we will actually. We will see it. But we're not going to deal with changing accelerations. Well, I'll show you what I mean in a bit. Okay, so the instantaneous acceleration, just like we did before, it's based on that definition, the limit as delta t approaches 0 of delta v over delta t. In fact, you know, when Newton invented calculus, much of what he was doing it for was to look at the motion of objects. So the derivatives and the integrals are really useful for studying kinematics. Okay, so it's the limit of delta t approaches 0, delta v over delta t. Of course, that is the derivative by definition, dv dt. And it's also, you might not have gotten to this in Calc 1, but it's also the second derivative of the position function, right? The velocity was the derivative of the position function. The acceleration is the derivative of the velocity function. And so the acceleration is also the second derivative. Just do that derivative twice of the position function. We'll do some examples like that later, today or Friday. All right. The acceleration then is the slope of the tangent line, just like we had before. On a graph of v versus t, velocity versus time. All right, so need to get pretty good at drawing your tangent lines. Try sketching out a couple of tangent lines on this function where I have the 2 dots. Just take a second and sketch out what the tangent line should look like on that function. And then I'll draw them in just a second. Which one has a negative slope, the left one or the right one? Which one? Left one, right. So this tangent line looks something like that. This tangent line looks something like that. On a test where I'm asking you to find the slope of a tangent line, the answers will be very clearly distinguished. Because honestly, there is a little bit of what's like judgment call on drawing those tangent lines. If you calculate them, you get the tangent line by definition. But when you're just sketching them in, there's a judgment call. So I'll make sure the answers, if it's a multiple choice question, that the answers are well distinguished so you can make sure you know what the right answer is. Okay, let's see, I've already said this, but if the acceleration is constant, which is what we'll deal with, the average acceleration will always equal the instantaneous acceleration. All right, let's try doing some problems with functions. Let's say that I have this function, and I just want to know the velocity at t equal 3 seconds. Just take a second. I want you to find what is the velocity of this particle. The position of the particle is defined by this function, 3t plus 2t squared minus 4. And I want to know what is the velocity at t equal 3 seconds. What would you do in order to find the velocity of that object at t equal 3 seconds? Yeah. Okay, well, I have the position, and I want to find the velocity. So what do I, not the second derivative, but the first derivative, right? The velocity is, right. We're going to get to the acceleration. That will be the second derivative. So we're going to take the first derivative of that. Remember, you multiply the exponent by the coefficient, right? And then you subtract 1 from the exponent, and then that gives you your derivative. What's the derivative? 4t plus 3. I'm going to write as 3 plus 4t. All right, so I imagine like this is 3t to the 1. I say 1 times 3 times t to the 1 minus 1. That's t to the 0, which is 1. That's where my 3 comes from. I multiply 2 times 2. That gives me 4. And then this is t to the 2 minus 1, which is just t to the 1. So that's where that comes from. And then if I want to know the velocity at 3 seconds, I just plug that in. So what's the velocity at 3 seconds? Right, 4 times 3. That's 3 plus 12. That's 15 meters per second. Our derivatives won't be terribly more complicated than that. In fact, these problems should be pretty simple for you. You'll see in the homework that there's some slightly more complicated problems, but the derivatives themselves are very, very simple, just derivatives of polynomials, and not much more than that. What is the acceleration then at t equal 3 seconds? Everybody says all at once together? 4, right, very good. So I just take the derivative of this function, which is the derivative of this. 3 doesn't change, right, because it's a constant. So its derivative is 0 because it's not changing. Because derivatives tell us how things change, a rate of change. And the derivative of 4t is just equal to 4. That's 1 times 4 times t to the 1 minus 1. So it's just equal to 4 meters per second squared. You'll certainly see a question on the test where I just give you a function and I ask you some things about that. You might also have to integrate that function. You likely will. I'll show you how that works. I think next. You're going to see some qualitative things like this. Just describe the motion in these plots. So for example, I would ask you, is the velocity constant? Is it negative or positive? Is the acceleration negative or positive? And you should be able to tell me all those answers to things, to questions like that about a particular plot. So for example, here I have the position versus time graph. What is the velocity changing or constant in this graph? It's constant. The reason it's constant is because the slope is constant. Okay? Is the velocity in the positive direction or the negative direction for this graph? It's in the positive direction. How do we know it's in the positive direction? It has a positive slope. So if it were like this, for example, it would be a negative slope. What is the acceleration? Is the acceleration positive, negative, or 0? It's 0. Why is it 0? Because the slope is constant. That means the velocity is not changing. If the velocity is not changing, the acceleration is 0. Okay? Yeah, with me? That's pretty simple, right? Let me write that down. So here I have a positive velocity. I have a constant velocity. And I have an acceleration equal to 0. All right, how about this next one? Does it have a positive or a negative velocity or zero velocity for this one? It has a positive velocity. Is that velocity increasing or decreasing or staying the same? What do you think? Increasing, decreasing, or staying the same? Here are a couple increasing. How do you determine if it's increasing, decreasing, or staying the same? You look at what? You look at the slope, and you ask yourself, how is the slope changing? And initially, the slope of the tangent line is like this, and then it gradually gets bigger and bigger. All right, so the slope of this line is increasing. That means the velocity is increasing. Okay? The acceleration of this graph, is it positive, negative, or zero? Positive, because my velocity is positive and my velocity is increasing. If my velocity is positive, my velocity is increasing, that gives me a positive acceleration. So I have a positive velocity, I have an increasing velocity, and I have a positive acceleration because v is going up and v is positive. Go back to those rules, right, that we had before. All right, this next one's pretty simple. What can you tell me about this object? It's not moving at all. No velocity. It's not accelerating either. All right, so the velocity is 0. It's unchanging. The acceleration is 0. Let's try another one. Okay, how about this one? The one on the left. Positive or negative velocity? Positive velocity. It has a positive slope. Increasing or decreasing velocity? Decreasing. The slope is getting smaller. Positive, negative, or 0 acceleration? Negative acceleration. Very good. It's negative because the velocity is positive and it's decreasing. The velocity is positive and the velocity is decreasing. That means the acceleration is in the opposite direction of the velocity, so it's a negative acceleration. All right, so I have a positive v, I have a decreasing v, and I have a negative acceleration for this case. This other one's pretty simple. Here I have a negative velocity, acceleration is equal to 0, and here I have a positive velocity, acceleration is equal to 0. Okay, and then we have the v versus t graphs. These are velocity versus time graphs. We're going to also have to interpret some of these. Well, maybe we'll look at an old exam question. Um, Tell me about this velocity. Is it increasing or decreasing or staying the same? Increasing, right. Is it positive or negative? It's positive. Why do we know it's positive, y'all? It's not the slope, it's the first quadrant. All right, because this is velocity versus time. The velocity is positive simply because it's in that first quadrant. If it were down in this part in this quadrant, it would be negative. All right, that was kind of tricky. What about the acceleration? Is the acceleration positive, negative, or 0? It's just the slope, right? Listen, guys, the slope of a position versus time graph is the what? Velocity. The slope of a velocity versus time graph is the what? Acceleration, right. So here, my acceleration is positive because the slope is positive. So I have a positive velocity. That's because I'm in the first quadrant. I have an increasing velocity, right, just because it gets bigger, right, as you proceed with time. And I have a positive acceleration. That's because the slope is positive. All right, I'm going to give you the answer for these here. I have a positive velocity for the same reason it's in the first quadrant. The acceleration is what? Positive or negative or 0? It's equal to 0, right? Because the slope is 0. And then these are just a combination of those. This is a negative acceleration. This is acceleration equal to 0. We can move on? No? Let's try this quick test. Which of these plots is impossible? Just to help you think about plots and what they represent. All right, I'll stop at 25. 25. Awesome. B is the right answer. Why is B the right answer? Oh, right. Yeah. And plus, you can't be in two places at once. Like at this time, you would be both here and here. But yeah, the time goes backwards. That's kind of funky. All right. Uh, let's see. Oh yeah. So a pony walks into a bar and says, "Bartender, can I have a drink?" And the bartender says, "What?" And the pony says, "Can I have a drink?" He says, "What?" And the bartender says, "What?" And the pony says, "Oh, I'm sorry. I'm just a little horse." There, get it. Pony, little horse. All right. Uh, let's try that. I think there's another one here. Park is running slowly in gym class, but then he notices Jenna watching him, so he speeds up to try to impress her. Which of the graphs could represent his motion? And if you get this one right above 90%, I'll tell you a little story about my wife and I before we got married when I was trying to impress her. But you have to get above 90%. All right, I'm going to stop at 45. Okay, C is a right answer. We're going to count that. I will tell you the story. But what other of these could possibly be the answer as well? C is the right answer because I have a small slope and then I have a big slope, right? Small slope, big slope. Which other of these fits that bill? It could be D as well. Nobody put D. That's unfortunate. But this one could be. It's just he'd be running to the left instead of the right, right? Small slope, big slope. Slow, speed it up. Are you want to hear the story? All right. A few months before my wife and I were married, we uh we were in grad school together, and we had like 3 floors in the building where we were, and we'd go back and forth on the stairwells. And I was trying to impress her, and the way I impressed her, because guys like to do this when they're courting a lady, that I would jump from the top step all the way down to the bottom step. It was like 10 steps, and I would do it with no hands. I was just it was like one of those what are they guys? Those guys parkour or whatever. It was like that. And she's like, "Gosh, this guy is." Way cool, right? And so I did this. I had done it a lot before because I often went on these stairwells. But one day we were on a stairwell that didn't usually travel on, and I did that. And there was this wall that came down over the stairwell, and it was very sharp, like this, 90-degree angle, and it caught me right here in midair, and it knocked me back, and I was able to sort of get up, and she looked at me. She's like, "Chad, are you okay?" I said, "Yeah, I'm just fine." And just as I said that, your head, man, a lot of blood in your head, right? Stream of blood came down and like dripped off my nose onto the thing, and then it's just like it was like a gusher coming open. And she's like, "Chad, you have blood coming down your head." And I'm like, "Oh." And so there was a shower on the 13th floor. So I went, zoomed down to the 13th floor. I said, "I got to get out of here." So I zoomed off and I left her. And it took me like half an hour to get all the blood out of my hair and off of me. Uh, and of course, in that time, she of course thought I was what, dead or whatever. Yeah. So she was terrified. But everything was okay. She was impressed. And then, the rest is just history. Okay, let's look at some kinematics equations. And I want to show you how to derive the kinematics equations. No, I don't think you know how to derive them, but I'm going to show you how to derive them. They're pretty simple derivations. They're based on a couple definitions. The definition here is just that A is dv dt. Right? We've already seen that definition. The acceleration is the derivative of the velocity with respect to time. And so we can write this again and say that dv is equal to a dt, and then the integral of dv dt is just the integral of a dt. Now, if a is not changing with respect to time, what is the integral of a dt? The indefinite integral. Not 0, no. I can further write this because a is not changing with time. I can just write it like this. It's the integral of dt. What's the integral of dt? T, right. It's just equal to t. The integral of dt is equal to t. So this is just equal to at. I know a lot of you have not had integral calculus. Is that right? You know, sort of know what I'm talking about here with the integrals? We covered it a little bit in the beginning. Um, it's equal to at, but everybody knows whenever you do an indefinite integral, which is what this is, what do you have to include? Plus c is your integration constant. Mathematicians call it an integration constant, but really it's just an initial condition, right? An integration constant is just an initial condition, and since in this case we're talking about v, we're going to add our integration constant, but instead of calling it c, we're going to call it v naught. That's our initial velocity. So v then, I'm going to rewrite it the way I normally do, is just the initial velocity plus the acceleration times the time. You don't need to memorize this equation or just know the derivation because it's a really simple derivation and you can just derive it. But I recommend that you just take a little note card and write this equation and the next one on it. And there aren't that many equations, honestly, for this next test. And just paste it to your mirror or above your kitchen sink or wherever it is that you look a lot. And then you'll know them by a couple of days. Then you can tear them down. All right? Or you write them on your hand if you want to do that right now. Um, so we know that v is equal to v naught plus at. And then the next definition comes from this, or the next equation comes from this definition, which is just velocity is the derivative of the x position with respect to time. Then dx is equal to v dt, right? Just like we did before. That's going to, and then if I take the integral, that's going to be the integral of v dt. The integral of dx is just x, so this just carries down to x. And then I know now that v is dependent upon t in this way from that previous definition. All right, so I just plug that in here, and then I can break this apart into separate integrals. Goes the integral of v naught dt plus the integral of at dt. All right, the integral of v naught dt is what? Because v naught doesn't change with time, so it's just going to be what? V naught t. All right, so this is just going to be v naught t. What is the derivative of at dt? Let me remind you how to do the derivative. If we have the derivative of at to the n dt, it's going to be, shoot, what is it? A t to the n plus 1 divided by n plus 1. Isn't that right? Did I get that right? I think it is. All right, so what's going to be the derivative of this function? 1/2 at squared. Here, n is equal to 1, and so it's going to be, a is also equal to 1, but it's going to be n plus 1. That'll be 1 plus 1 is 2, and then I'm going to have a 2 in the denominator as well. So it's going to be v naught t plus 1/2 at squared. And I also have to have that integration constant, which we're going to call what? What is our integration constant for this function? It's going to be x naught. Remember, integration constants, despite what the mathematicians might tell you, they're just initial conditions. And the initial condition for this position is just the initial position. All right, so it's going to be plus x naught. All right, so normally this is written with the x naught first. In fact, usually x naught will equal 0, and so we'll just leave it there. Let me give you this other equation. We're not going to use it. Oh, no, it's already written here. You can substitute one equation into the other and get this one, And a lot of physics textbook will give you this, but I don't use it. It's just another equation to memorize. It comes from those two very basic equations. And I think you'll find as we work through problems on Friday that you don't really need that equation. All right? We're going to work through some more complicated problems on Friday, so make sure that you attend, and I'll see you on Friday. You have a great day. All right, remember, if you want to come to that help session, it's on Thursday.